Time is interesting. You could spend time, take time, lose track of it, give it away, use it wisely, waste it. Time is of the essence, time is running out, etc., etc. But try explaining time to someone. Try drawing a picture of it, or containing it, or manipulating it in some way. It's not going to happen. But there's no doubt that we experience time, right? I mean, we could observe the present moment, remember the past, and we're always sensing the flow of time. But is it actually a real thing? Is there any way to prove that time exists, like how that chair exists, or that you or I exist, or that that palm tree exists, however briefly, because it's dying? Sorry. For ancient civilizations, time was nothing more than the passing of the sun or the changing of the seasons. It was markings on calendars or the position of a shadow on a sundial. But as technology and timekeeping devices evolved, so did our perception of time. Instead of just counting the days or the swings of a pendulum or the movement of a minute hand, it seemed as if we were counting time itself. Then came along Sir Isaac Newton, and in addition to getting hit in the head by a fictitious flying apple, he also had a thing or two to say about physics stuff. He's probably most famous for his laws of motion, but he was also one of the first to suggest a realist view of time. According to Newton, time was absolute, true, universal, and flowed at a constant rate, independent of any change that we were able to see. This absolute notion of time was critical for the accuracy of Newton's laws of motion, and for a while his ideas formed the basis of our entire understanding of the universe. Sir Isaac Newton was a badass. Now don't get me wrong, Newton's laws of motion were awesome, but they're unable to account for the strange properties of light. At the end of the 19th century, what puzzled scientists was the fact that the speed of light appeared to be constant, no matter how fast the light source or measuring device was traveling. In fact, it doesn't matter if you're standing still or moving away or even traveling towards a light source. The speed of light will always stay the same. This defied all logic at the time and couldn't be explained by the physical laws that were defined by Sir Isaac Newton. A new, deeper understanding of physics was needed. Enter Mr. Albert Einstein. In 1905, Albert Einstein, only 26 years old at the time, published a theory that revolutionized physics and changed the way that we understood our universe. It was called the unremarkable theory of relativity. Special theory of relativity. I'm not going to talk too much about special relativity. There are already a lot of great videos on the subject, links in the doobly-doo. But essentially, according to Einstein, objects traveling at high speeds will actually experience time slower than objects at rest. This is called time dilation, and it has been proven experimentally. In particle accelerators, certain particles have a longer lifespan because they're traveling at speeds close to the speed of light. Atomic clocks on planes run slower than clocks on the ground, and GPS satellites have to be constantly corrected for time dilation. General relativity, Einstein's hit sequel to special relativity, says that time is also affected by gravity. In fact, gravity is really just the warping of space and time in the presence of a massive object. That's why objects in space orbit bigger objects, and that also causes clocks in strong gravity to experience time slower than clocks in weaker gravity. This effect is noticeable in GPS satellites, and technically, according to general relativity, your head is actually slightly older than your feet. Slightly. So it would appear that Sir Isaac Newton, though right about a lot of things, was wrong about time. Time is not this static universal thing, it's constantly changing and fluctuating.
Suppose Adam fires a laser at the ground, which bounces off a mirror, and he measures the time it takes for the light to return to the spaceship. From Adam's perspective, the laser light goes straight up and down. From Sarah's perspective, the laser light follows a V-shaped path. The V-shaped path is longer than the straight up and down path. Since the speed of light is the same for all observers, from Sarah's perspective it takes a longer amount of time for the laser light to return to the spaceship. But if Sarah looks at Adam's clock, she will see that his clock reads less time in between when he fired the laser and when he received the reflected light back. This means that Sarah will see Adam's clock running slower than her own clock. The closer that a spaceship approaches the speed of light, the slower the time inside the ship will flow. If the speed of the spaceship was equal to the speed of light, then time inside the ship would stop altogether. No matter how fast the spaceship travels, Adam will never notice that time for him is going slower. Everything is slower by the exact same amount, including the speed of his thoughts. So time for Adam appears to be flowing normally. From Adam's point of view, his ship is standing still, and it's the rest of the universe that's moving. Therefore, Adam will think that everyone else's clocks are moving slowly. Suppose there are 3 ships moving together, and Adam fires a laser to the 2 other ships. From Adam's perspective, all 3 ships are standing still, and the 2 other ships will receive the laser light at the same time. Sarah sees the light from both lasers move at the same speed. Therefore, Sarah will see the left ship receive the laser light before the right ship. But we know that the clocks on the 2 ships read the same time when they each receive the laser light. This means that Sarah must see the clock on the left spaceship running ahead of the clock on the right spaceship. From Sarah's point of view, time on the left ship is running ahead of time on the right ship. From Adam's point of view, the time on both ships is the same. Suppose that Adam sends a command for all the ships to fire their engines at the same time. From Adam's point of view, all the ships accelerate together, and the distance between them stays the same. From Sarah's point of view, time on the left ship is running ahead of time on the right ship. Sarah will see the left ship accelerate first, and the right ship accelerate last, and the distance between the ships will shrink. Each spaceship can be thought of as being made up of smaller spaceships, with the distance between them shrinking as they move faster. The closer a spaceship approaches the speed of light, the shorter it becomes. No matter how fast the spaceship travels, Adam will never notice that his spaceship has gotten shorter. Everything inside the spaceship has gotten shorter by the exact same amount, including Adam himself and all his rulers, so everything inside the spaceship will look normal to Adam. When Adam fires his rockets, the acceleration causes him to be thrown back in his seat. From his point of view, the spaceship is standing still, and it's the rest of the universe which is accelerating. From his point of view, there must be a gravitational field causing the entire universe to accelerate. From Adam's point of view, it is this gravitational field which is causing him to be thrown back in his seat. From Adam's point of view, the force from his rockets exactly balances the gravitational force, causing his ship to stay in the same place. Adam sees the entire universe affected by this gravitational field, including rays of light. Since light must be the same speed for all observers even though it is affected by gravity, this means that gravity must also affect the rate at which time flows. If Adam travels near the speed of light, then time on his ship will flow very slowly. When Adam returns, only a few minutes will have passed for him, but many years will have passed for Sarah. From Adam's point of view, he's standing still, and it's time on Earth which is moving slowly. When Adam fires his rockets to turn around, he will think there is a gravitational force causing him to remain still and causing the Earth to accelerate towards him. From Adam's point of view, this gravitational field is causing time on Earth to run faster than time on his ship. This is why, from Adam's point of view, more time has passed for Sarah than for him. Gravity is not a force, but a curvature in space-time. Objects with mass cause a curvature in space and time. There only appears to be a force, when in reality everything is just following straight lines.